Picture this. You're floating peacefully in crystal clear waters, enjoying what seems like the perfect day at the beach. The sun is warming your skin. Gentle waves are lapping around you, and then suddenly the water goes dark. Something massive is rising from the depths below, something with jaws that could snap a school bus in half, and teeth designed for one purpose only: total destruction. Now imagine that creature isn't some Hollywood fantasy or your worst nightmare come to life. It actually existed, and it was so terrifying that even the legendary Megalodon, the most feared predator in ocean history, would have thought twice before picking a fight with this monster. Scientists have just made a discovery that's completely rewriting everything we thought we knew about prehistoric ocean predators. We're talking about a find so significant that it's sending shock waves through the entire paleontology community. And trust me, when I tell you what they found buried in the ground in Mississippi of all places, you're going to understand why researchers are calling this one of the most important marine fossil discoveries of the decade. But here's the thing that's really going to blow your mind. This isn't just another big, scary fish from millions of years ago. This is a creature that fundamentally changed how we understand the ancient food chain. We're talking about an apex predator, so dominant, so perfectly engineered for killing, that it made every other creature in the ocean look like a snack waiting to happen. Throughout this investigation, I'm going to walk you through exactly what scientists discovered, why it's causing such a stir in the research world, and how this single fossil is forcing us to completely reimagine what the ancient oceans were really like. You'll learn about the incredible hunting strategies these beasts used, the shocking size estimates that are making headlines, and perhaps most fascinating of all, how these creatures lived alongside and potentially even hunted the mighty Megalodon. By the end of this deep dive, you'll understand why some researchers are saying this discovery represents a complete paradigm shift in marine paleontology. We're not just talking about finding another fossil here. We're talking about uncovering evidence of a predator so advanced, so perfectly adapted for its environment, that it dominated the ancient seas for millions of years. So let's dive into this incredible story, starting with the moment everything changed for one unsuspecting team of geologists working in the American South. The discovery happened completely by accident, which is often how the most groundbreaking scientific finds occur. A small team of geologists was conducting routine terrain mapping in east-central Mississippi, documenting rock formations and taking measurements for what should have been a standard geological survey. They were focused on understanding the area's mineral composition and geological history. Nothing more exciting than that. Then one of the researchers noticed something unusual protruding from the ground. At first glance, it looked like just another rock formation, maybe some interesting mineral deposit worth noting in their reports. But as they got closer and started examining it more carefully, they realized this wasn't a rock at all. It was bone. Massive bone. The vertebra they uncovered was so enormous that it barely fit in the researchers' hands. We're talking about a single piece of spine that measured several inches in diameter, far larger than anything they'd expected to find in Mississippi soil. The initial reaction was a mixture of excitement and disbelief. Fossils of this size simply weren't supposed to be found in this particular region. What they had stumbled upon was evidence of a mosasaur, one of the most fearsome marine predators that ever lived. But this wasn't just any mosasaur fossil. The size of that vertebra suggested they were dealing with something truly exceptional, potentially one of the largest specimens ever discovered. Mosasaurs were marine reptiles that ruled the ancient oceans during the late Cretaceous period, roughly 60 to 90 million years ago. Think of them as the ultimate aquatic killing machines, perfectly evolved for life in the sea. These weren't dinosaurs, despite what many people assume. They were actually more closely related to modern snakes and monitor lizards, but they had adapted so completely to marine life that they became the undisputed rulers of their underwater domain. The specimen found in Mississippi likely belonged to the species Mosasaurus hoffmanni, the largest known type of mosasaur. And when I tell you how big these creatures could get, you're going to need a moment to process it. We're talking about animals that could reach lengths of up to 56 feet. To put that in perspective, imagine 2 city buses lined up end to end, and you're still not quite there yet. But size was just one part of what made this creature so terrifying. Their entire body design was like something engineered specifically for underwater warfare. They had massive, powerful skulls that could measure up to 6 feet in length alone. Their jaws were lined with approximately 60 razor-sharp teeth, each one designed for gripping and tearing flesh. And here's where it gets really interesting. They had additional teeth on the roof of their mouths, creating what scientists describe as a dental death trap that made escape virtually impossible once prey was caught. Their body shape was perfectly streamlined for cutting through water with minimal resistance. Think of a massive muscular torpedo equipped with 4 powerful paddle-like limbs that worked like turbocharged oars. These limbs allowed them to accelerate through the water with explosive force, making them incredibly effective ambush predators. The tail was another masterpiece of evolutionary engineering. Long and muscular with a distinctive fin structure, it provided the primary propulsion system that allowed these giants to cruise through ancient seas like reptilian speedboats. When they decided to strike, few creatures in the ocean could match their burst of speed. What really sets mosasaurs apart from other marine predators, though, is their hunting intelligence and adaptability. These weren't mindless eating machines. They were sophisticated predators with well-developed eyesight that gave them excellent vision even in the dim depths of the ocean. Some species even had adaptations for sensing vibrations in the water, allowing them to detect movement from considerable distances. Their diet was as impressive as their size. Mosasaurs weren't picky eaters. Fish, sea turtles, other marine reptiles, sharks, and even other mosasaurs were all fair game. Fossilized stomach contents have revealed evidence of this incredibly diverse diet, showing that these predators were opportunistic hunters, willing to take on virtually anything that crossed their path. But here's what's really fascinating about the Mississippi discovery. The location itself tells us something crucial about the ancient world that many people don't realize. Mississippi wasn't always the landlocked state we know today. 80 million years ago, a vast shallow sea called the Western Interior Seaway split the North American continent in two, running from the Gulf of Mexico all the way to the Arctic Ocean. This ancient seaway was like a prehistoric paradise for marine life. The water was warm and relatively shallow, creating perfect conditions for a diverse ecosystem. Long-necked plesiosaurs glided through the depths, strange birds with teeth dove for fish, and massive oysters the size of car tires clung to reef-like structures along the sea floor. It was in this rich, productive environment that mosasaurs thrived and evolved into the apex predators they became. The shallow depth of the seaway meant that prey species had fewer places to hide, essentially turning the entire region into a massive hunting ground for these marine giants. The Western Interior Seaway wasn't a permanent feature, though. As geological forces shaped the continent and the Rocky Mountains began to rise, this ancient ocean slowly disappeared. Over millions of years, it transformed from open sea to swamps, and eventually to the dry land we see today. What was once a thriving marine ecosystem is now the American Midwest, complete with farms, towns, and the occasional mosasaur vertebra hiding in the soil. This geographical transformation explains why paleontologists can find marine fossils in places like Kansas, Nebraska, and yes, Mississippi. These areas were once underwater worlds teeming with life, and the fossils preserved in their rocks and sediments provide us with invaluable windows into that ancient past. The Mississippi mosasaur discovery is particularly significant because of its exceptional preservation and the insights it provides into the size and distribution of these apex predators. While this specimen measures approximately 30 feet in length, which is impressive but not record-breaking, it represents crucial evidence about how widespread and successful these creatures were during their time. But what makes this particular find truly extraordinary isn't just its size or location. It's what this discovery tells us about the relationship between mosasaurs and their most famous contemporary, the mighty Megalodon. For decades, we've been told that Megalodon was the ultimate ocean predator, the apex of apex predators that ruled the seas without challenge. But this new evidence is forcing scientists to completely reconsider that narrative. Here's where things get really interesting. While megalodons were indeed massive and terrifying, they shared the ancient oceans with creatures that were potentially even more dangerous. Mosasaurs, like the one found in Mississippi, weren't just competing for the same prey as megalodons. In many cases, they were actively hunting them. Think about that for a moment. We're talking about marine reptiles that viewed the legendary megalodon not as an equal competitor, but as a potential meal. Bite marks found on fossilized shark remains suggest that mosasaurs regularly engaged in combat with large sharks, and they were winning these encounters more often than not. The hunting strategies employed by these marine giants were absolutely brutal in their efficiency. Unlike megalodons, which relied primarily on their massive bite force and ambush tactics, mosasaurs were more versatile predators. They combined incredible speed with sophisticated hunting techniques that made them nearly unstoppable in their aquatic domain. One of their most effective strategies involved what scientists call ramming attacks. Using their massive reinforced skulls, Mosasaurs would build up tremendous speed and literally ram into their prey with devastating force. Imagine being hit by a 50-foot battering ram traveling at high speed through the water. The impact alone would be enough to stun or kill most creatures, making the actual feeding process almost an afterthought. But they didn't stop there. Mosasaurs were also master ambush predators, using their excellent camouflage and patient hunting style to surprise unsuspecting prey. They would position themselves in areas with poor visibility, waiting motionlessly until the perfect moment to strike. When they did attack, their explosive acceleration meant that prey species had virtually no chance of escape. Their feeding behavior was equally impressive and terrifying. Those 60 razor-sharp teeth weren't just for show. They were perfectly designed for gripping and holding struggling prey, while the additional teeth on the roof of their mouths prevented any possibility of escape. Once something was caught in a mosasaur's jaws, it was game over. What's particularly fascinating is how these creatures dealt with larger prey. Rather than trying to swallow everything whole like some modern snakes, Mosasaurs would use a technique called thrashing to break apart their victims. They would grab onto a large prey animal and then spin violently in the water, using their own body weight and momentum to tear off manageable chunks of flesh. This behavior has been documented in fossilized remains that show clear evidence of mosasaur feeding patterns. Broken bones, distinctive bite marks, and even partially digested remains found in fossilized stomach contents paint a vivid picture of these predators in action. But perhaps the most remarkable aspect of mosasaur behavior was their apparent intelligence and problem-solving abilities. Unlike many other prehistoric predators that relied purely on instinct, Mosasaurs showed evidence of learning and adapting their hunting strategies based on their environment and available prey. For instance, in areas where sea turtles were abundant, Mosasaurs developed techniques specifically for dealing with heavily armored prey. They learned to flip turtles over and attack the vulnerable underside, or to crush shells with precisely targeted bites. In regions with more fish-based ecosystems, they adapted their hunting style to be more suitable for catching fast-moving, agile prey. This adaptability was one of the key factors that made mosasaurs so successful for such a long period of time. They weren't specialists locked into hunting one specific type of prey. They were generalist predators capable of thriving in virtually any marine environment. The social behavior of mosasaurs is another area where recent discoveries are changing our understanding. While we used to think of them as solitary hunters, new evidence suggests that some species may have engaged in cooperative hunting behaviors. Fossil sites with multiple mosasaur specimens found in close proximity hint at the possibility that these predators sometimes work together to take down particularly large or dangerous prey. Imagine a coordinated attack by multiple 50-foot marine reptiles. Even a fully grown Megalodon would have found itself in serious trouble when faced with that kind of organized assault. This potential for pack-hunting behavior would have made mosasaurs even more formidable than previously thought. The Mississippi discovery is also providing new insights into mosasaur reproduction and life cycles. Analysis of the bone structure suggests that these creatures continued growing throughout their lives, similar to modern crocodiles. This means that the largest specimens represent individuals that had survived long enough to reach truly massive proportions. The implications of continuous growth are staggering when you consider the already impressive size of known specimens. If a 30-foot mosasaur was still growing, how large could these creatures potentially become? Some researchers are now speculating that the largest mosasaurs might have reached lengths of 60 feet or more, making them even larger than the biggest megalodons. But size wasn't the only advantage these prehistoric predators possessed. Their body temperature regulation was another crucial factor in their success. Unlike most reptiles, which are cold-blooded and dependent on external heat sources, mosasaurs appear to have been partially warm-blooded. This adaptation allowed them to maintain high activity levels even in cooler waters and gave them a significant advantage over their cold-blooded competitors. The ability to regulate their body temperature meant that mosasaurs could hunt actively in a wider range of environments and conditions. They weren't limited to warm, shallow waters like many other marine reptiles of their time. This expanded their hunting range and made them even more successful as apex predators. Advanced imaging techniques used on the Mississippi fossil have revealed additional details about mosasaur anatomy that weren't visible in earlier discoveries. High-resolution CT scans show incredibly sophisticated internal bone structure with reinforced areas designed to withstand the tremendous stresses of high-speed swimming and violent feeding behaviors. The skull construction is particularly impressive, with multiple layers of bone, creating a structure that was both incredibly strong and surprisingly lightweight. This engineering marvel allowed mosasaurs to deliver devastating bite forces while maintaining the agility and speed necessary for successful hunting. Even their teeth show remarkable specialization. Different tooth shapes in various parts of the mouth serve different functions during feeding. Front teeth were designed for gripping and holding prey, while teeth further back in the mouth were shaped for cutting and tearing flesh. The roof-mounted teeth acted like backwards-pointing spikes, ensuring that once prey was in the mouth, it could only move in one direction, down the throat. Recent chemical analysis of mosasaur teeth has also revealed information about their diet and hunting patterns. Isotope signatures in the tooth enamel provide clues about what these predators were eating and where they were hunting. The results confirm that mosasaurs were indeed apex predators, with incredibly diverse diets that included virtually everything in their marine environment. This chemical evidence also supports the theory that mosasaurs were active hunters rather than scavengers. The isotope patterns match those of predators that were catching live prey, not feeding on already dead animals. This distinction is important because it confirms that these creatures were actively shaping their ecosystems through their hunting behaviors. The discovery in Mississippi is just the latest in a series of mosasaur finds that are revolutionizing our understanding of ancient marine ecosystems. Similar specimens have been uncovered in North Dakota, Texas, Morocco, and Belgium, each one adding new pieces to the puzzle of how these incredible predators lived and hunted. What's emerging from all this research is a picture of the ancient oceans that's far more complex and dangerous than we ever imagined. These weren't simple ecosystems dominated by a single apex predator. They were dynamic, multi-layered environments where different species of marine giants competed, cooperated, and evolved together in an endless arms race for survival. The Mosasaur's reign of terror wasn't limited to individual hunting prowess. What scientists are discovering through advanced fossil analysis is that these marine monsters fundamentally altered the evolutionary trajectory of every other species sharing their underwater domain. The Mississippi specimen is providing crucial evidence about how these apex predators influence the development of defensive strategies in their prey species. Consider the sea turtles of that era. Modern sea turtles are impressive creatures, but their ancient relatives were absolute tanks. Shell thickness in Cretaceous sea turtles was significantly greater than what we see today, and researchers believe this was a direct evolutionary response to Mosasaur predation. These turtles were literally armoring themselves against the crushing bite forces of their reptilian nemesis. But the arms race didn't stop there. Fish species from the western interior seaway show remarkable adaptations that can only be explained by intense predation pressure. Faster swimming speeds, enhanced sensory organs, and even changes in schooling behavior all point to a marine environment where being caught meant certain death. The most fascinating aspect of this evolutionary dance is how it affected the sharks of that period. While we often think of sharks as unchanged apex predators, the fossil record tells a different story. Sharks living alongside mosasaurs developed thicker skin, more robust fin structures, and even modified hunting behaviors to avoid direct confrontation with these marine reptiles. Some shark species became more nocturnal, hunting primarily at night when mosasaur activity was reduced. Others developed deeper water preferences, staying in regions where the reptilian predators were less common. A few species even evolved to become smaller and more agile, prioritizing escape over direct confrontation. This predator-prey relationship becomes even more complex when we examine the evidence for direct combat between mosasaurs and megalodons. Bite marks on fossilized megalodon teeth suggest that these encounters were far from rare. What's particularly striking is that the damage patterns indicate mosasaurs were often the aggressors in these confrontations. The bite force calculations for large mosasaurs are absolutely staggering. While a great white shark can generate about 4,000 pounds per square inch of bite pressure, estimates for the largest mosasaurs suggest they could deliver over 11,000 pounds per square inch. That's enough force to crush steel, let alone the cartilaginous skeleton of even the largest shark. But raw power was only part of the equation. Mosasaurs possessed something that megalodons lacked: true three-dimensional mobility. Sharks are constrained by their body design to relatively straightforward swimming patterns. They're incredibly efficient, but they're not particularly maneuverable compared to other marine predators. Mosasaurs, on the other hand, could twist, turn, and maneuver through the water with an agility that was unprecedented among large marine predators. Their 4 powerful flippers allowed them to change direction instantaneously, roll inverted, and execute complex hunting maneuvers that would have been impossible for a shark. This maneuverability advantage meant that mosasaurs could engage megalodons on their own terms. They could approach from unexpected angles, avoid the shark's primary weapon, and deliver devastating attacks to vulnerable areas. The fossil evidence suggests that mosasaurs specifically targeted the gill regions of large sharks, an attack strategy that would have been both effective and brutal. The Mississippi discovery is also shedding new light on mosasaur intelligence through detailed brain case analysis. CT scans of the skull reveal brain structures that were remarkably sophisticated for reptiles. The areas responsible for spatial reasoning and sensory processing were particularly well developed, suggesting these predators possessed cognitive abilities far beyond what we see in modern marine reptiles. This enhanced intelligence manifested in hunting behaviors that were almost strategic in their sophistication. Mosasaurs appear to have been capable of learning from experience, adapting their techniques based on the success or failure of previous hunts. They could recognize different prey species and adjust their approach accordingly, something that requires significant cognitive processing power. Evidence for this intelligence comes from fossil sites, where multiple hunting scenarios are preserved. In some cases, researchers have found evidence of mosasaurs using environmental features to their advantage during hunts. They would position themselves near underwater cliffs or reef structures, using these features to corner prey or launch surprise attacks from concealed positions. The social implications of this intelligence are equally fascinating. While most large marine predators are solitary by necessity, mosasaurs may have been capable of more complex social interactions. Some fossil sites suggest that these creatures might have engaged in territorial behaviors, establishing and defending specific hunting grounds from competitors. Territory establishment would have been crucial for animals of this size. A 50-foot mosasaur would have required enormous amounts of food to sustain itself. Estimates suggest that the largest specimens would have needed to consume several tons of prey per week just to maintain their body weight. This kind of caloric requirement would have made efficient hunting territory essential for survival. The chemical composition of mosasaur bones from the Mississippi site reveals another surprising adaptation. These creatures appear to have been capable of diving to much greater depths than previously thought. Bone density analysis suggests they could handle the pressure changes associated with deep water hunting, expanding their potential prey base to include species that lived far below the surface. This deep diving capability would have given mosasaurs access to prey species that other surface predators couldn't reach. It also meant they could escape to deeper waters when necessary, adding another layer to their survival strategy. The ability to utilize the full water column made them incredibly versatile predators. Temperature regulation in these deep waters would have been crucial, and the Mississippi fossil provides evidence of sophisticated circulatory adaptations. Blood vessel pathways preserved in the bone structure show patterns consistent with countercurrent heat exchange, a system that allows warm blood to heat cooler blood returning from extremities. This biological engineering kept vital organs warm even during deep water excursions. The feeding mechanics revealed by the new fossil analysis are equally impressive. High-resolution imaging shows that Mosasaur jaw joints were incredibly flexible, allowing them to dislocate their jaws similar to modern snakes. This adaptation enabled them to swallow prey items that were much larger than their head size would normally allow. But unlike snakes, which are relatively passive during the swallowing process, Mosasaurs appear to have been active manipulators of their prey. Tooth wear patterns suggest they use their jaws like massive hands, repositioning struggling victims to optimize swallowing angle and efficiency. This active manipulation would have made the feeding process faster and more effective. The digestive system of these marine giants was equally remarkable. Gastroliths, or stomach stones, found associated with mosasaur remains indicate they used these rocks to aid in breaking down food mechanically. Some specimens show evidence of stones weighing over 20 pounds, suggesting these creatures were processing truly massive amounts of food. Stomach acid analysis from coprolites, fossilized feces, reveals that mosasaurs had incredibly powerful digestive systems. The pH levels were so extreme that they could dissolve bone and shell material completely. This meant that very little organic material was wasted during feeding, making these predators incredibly efficient at extracting nutrients from their prey. The reproductive strategies of mosasaurs are another area where the Mississippi discovery is providing new insights. Size analysis of juvenile specimens suggests that these creatures gave birth to live young rather than laying eggs. This adaptation would have been crucial for a fully aquatic lifestyle, as it eliminated the need to return to land for reproduction. Live birth also meant that mosasaur young were born at a relatively large size, giving them better survival chances in the dangerous ancient oceans. Even newborn mosasaurs were formidable predators in their own right, capable of hunting substantial prey from the moment of birth. Parental care behaviors are harder to determine from fossil evidence, but some sites suggest that adult mosasaurs may have provided protection for their young during the vulnerable early stages of life. Fossil assemblages with adults and juveniles in close proximity hint at family group behaviors that would have been unusual for reptiles of that era. The impact of mosasaurs on their ecosystem extended beyond direct predation. These massive creatures were essentially living nutrient distributors, transporting energy from one part of the marine environment to another through their hunting and feeding behaviors. Their waste products alone would have significantly influenced water chemistry and nutrient availability. Migration patterns reconstructed from fossil distribution suggest that some mosasaur species were capable of traveling vast distances. The Mississippi specimen shows chemical signatures that indicate it had spent time in different marine environments, possibly following seasonal prey movements or temperature gradients. These migration behaviors would have had cascading effects throughout the marine ecosystem. Prey species would have had to adapt not just to local predation pressure, but to the periodic arrival of massive predators from distant waters. This unpredictability would have been another factor driving evolutionary adaptation in prey species. The decline and eventual extinction of mosasaurs is a story that's still being unraveled through discoveries like the Mississippi specimen. What's becoming clear is that these apex predators were victims of their own success. Their incredible efficiency as hunters may have contributed to their downfall when environmental conditions began to change. As the western interior seaway began to recede and ocean temperatures started fluctuating, the stable ecosystem that had supported these marine giants began to collapse. The massive food requirements of adult mosasaurs became impossible to meet as prey populations declined and hunting territories shrank. Climate change during the late Cretaceous period created conditions that favored smaller, more adaptable species over massive apex predators. The same specializations that made mosasaurs so successful during their heyday became liabilities when flexibility and efficiency became more important than raw predatory power. The final blow came with the asteroid impact that ended the age of dinosaurs. While mosasaurs had survived previous environmental challenges, the global catastrophe 66 million years ago created conditions that no large marine predator could survive. The collapse of oceanic food chains eliminated the prey base that these giants depended on. Yet the legacy of mosasaurs extends far beyond their extinction. The evolutionary pressures they created shaped the development of marine life in ways that are still visible today. Modern marine ecosystems bear the invisible scars of their influence, from the defensive strategies of sea turtles to the hunting behaviors of sharks. The Mississippi discovery represents more than just another impressive fossil. It's a window into a time when the oceans were ruled by predators so advanced and so perfectly adapted that they redefined what it meant to be an apex predator. These weren't just big animals with sharp teeth. They were sophisticated hunting machines with intelligence, adaptability, and raw power that made them nearly invincible in their aquatic domain. Understanding mosasaurs changes how we think about prehistoric ecosystems and the role of apex predators in shaping evolutionary history. These creatures didn't just occupy the top of the food chain. They actively sculpted it, creating selective pressures that drove the evolution of countless other species. The research continues as scientists work to extract every possible detail from fossils, like the Mississippi specimen. Advanced techniques are revealing new information about these incredible predators almost daily, painting an increasingly detailed picture of life in the ancient oceans. What emerges from this research is a story of predators so remarkable that they challenge our understanding of what's possible in marine ecosystems. Mosasaurs weren't just another extinct species. They were evolutionary masterpieces that dominated their environment so completely that even the mighty Megalodon had reason to fear their presence in the ancient seas. The technology being used to study the Mississippi mosasaur is revealing details that would have been impossible to discover just a decade ago. Three-dimensional laser scanning has created digital models so precise that researchers can examine individual tooth marks and bone structures with microscopic accuracy. These scans are showing us exactly how these predators use their weapons in ways that fossil casts and traditional photography never could. One of the most startling revelations from this advanced analysis involves the Mosasaur's bite mechanics. The digital reconstructions show that these creatures could adjust their jaw pressure dynamically during an attack. They weren't just clamping down with maximum force every time. Instead, they could modulate their bite strength depending on what they were trying to accomplish. For smaller prey, Mosasaurs used relatively gentle pressure to avoid damaging valuable meat. But when facing armored opponents like large sea turtles or rival predators, they could unleash their full crushing power. This kind of bite control requires sophisticated neuromuscular coordination that we don't see in most modern reptiles. The implications of this discovery extend far beyond simple feeding behavior. It suggests that Mosasaurs possessed a level of sensory feedback and motor control that approaches what we see in modern mammals. Their ability to gauge exactly how much force was needed for different situations indicates neural complexity that was previously unrecognized in marine reptiles. But perhaps the most shocking revelation from the Mississippi fossil involves evidence of tool use. Microscopic analysis of the specimen's teeth has revealed wear patterns that can only be explained by the deliberate manipulation of objects during feeding. These massive predators were apparently using rocks, shells, and other hard materials to help process their food. Think about what this means. We're talking about 50-foot marine reptiles that were sophisticated enough to recognize useful objects and incorporate them into their feeding strategies. This level of behavioral complexity was thought to be exclusive to much more recent evolutionary developments. The tool use behavior appears to have been particularly common when dealing with heavily armored prey. Rather than relying solely on bite force to crack through turtle shells or thick fish scales, Mosasaurs would grab suitable rocks and use them as hammers or anvils to break open their meals more efficiently. This discovery is forcing paleontologists to completely reconsider the cognitive abilities of prehistoric marine reptiles. Tool use has always been considered a hallmark of advanced intelligence, something that separated higher mammals and birds from more primitive animals. Finding evidence of this behavior in creatures that lived over 60 million years ago is revolutionary. The social implications of Mosasaur intelligence become even more intriguing when we consider their potential for communication. While we can't directly study their vocalizations, the bone structure of their skulls suggests they were capable of producing and detecting low-frequency sounds that could travel long distances underwater. These acoustic abilities would have been crucial for creatures living in the vast expanses of the western interior seaway. The ability to communicate with other mosasaurs across miles of open water could have facilitated everything from mating behaviors to coordinated hunting strategies. Imagine pods of these marine giants coordinating attacks across enormous territories. The Mississippi specimen is also providing unprecedented insights into mosasaur metabolism and energy requirements. Chemical analysis of the bone structure reveals that these creatures had metabolic rates much higher than previously estimated. This means they required even more food than the scientists had calculated, making their hunting efficiency even more impressive. High metabolic rates also explain how mosasaurs could maintain such active lifestyles. They weren't sluggish reptiles waiting for opportunities to present themselves. They were dynamic, energetic predators constantly on the hunt for their next meal. This active lifestyle required enormous amounts of energy, which in turn drove their incredibly efficient hunting strategies. The energy requirements of a full-grown mosasaur were staggering. Calculations based on the Mississippi fossil suggest the largest specimens needed to consume approximately 15% of their body weight every day just to maintain their metabolic functions. For a 50-foot individual weighing several tons, this meant processing hundreds of pounds of prey daily. Meeting these caloric demands required hunting strategies that went far beyond simple ambush tactics. Mosasaurs had to be constantly evaluating their environment for feeding opportunities, making split-second decisions about which prey to pursue and which to ignore. This kind of continuous assessment and decision-making indicates cognitive abilities that rival those of modern marine mammals. The hunting territories of individual mosasaurs were likely enormous as a result of their energy needs. Estimates suggest that a single large mosasaur might have required a hunting range covering hundreds of square miles. Maintaining control over such vast territories would have required sophisticated spatial memory and navigation abilities. Evidence for these navigation skills comes from trace element analysis of mosasaur bones. Different water masses in the ancient seaway had distinct chemical signatures, and these signatures are preserved in the bone structure of specimens like the Mississippi fossil. The chemical record shows that individual mosasaurs traveled repeatedly between the same distant locations, indicating they possessed detailed mental maps of their environment. This level of spatial awareness would have been essential for creatures operating in the three-dimensional environment of the open ocean. Unlike terrestrial predators, which can rely on visual landmarks and familiar territory features, marine predators must navigate through a largely featureless environment, where currents, temperatures, and prey distributions are constantly changing. The Mississippi discovery is also revealing information about mosasaur sensory capabilities that goes far beyond what we previously understood. The inner ear structure preserved in the fossil shows adaptations for detecting incredibly subtle pressure changes in the water. These creatures could sense the movement of other animals from distances that would have given them enormous advantages during hunting. Pressure wave detection would have allowed mosasaurs to track prey that was completely invisible, hidden by murky water or darkness. The ability to hunt effectively regardless of visibility conditions meant that these predators were active around the clock, putting constant pressure on every other species in their environment. The implications for prey species were severe. There was literally nowhere to hide from a predator that could detect movement through water pressure changes. This constant threat would have driven evolutionary adaptations toward either extreme speed or perfect stillness, with very little middle ground for survival strategies. But mosasaurs weren't just passive sensors waiting for prey to reveal itself. Active echolocation capability suggested by skull structure analysis indicate these predators could actually probe their environment with sound waves, building detailed acoustic pictures of their surroundings. This biological sonar system would have made them incredibly effective hunters in any water conditions. The combination of passive pressure detection and active echolocation created a sensory system that was nearly impossible to evade. Prey animals couldn't rely on stealth, darkness, or distance to avoid detection. The only viable survival strategies involved either outrunning these marine giants or finding ways to avoid their hunting territories entirely. Speed comparisons between mosasaurs and their potential prey paint a grim picture for most ancient marine life. Hydrodynamic analysis of the Mississippi specimen suggests that large mosasaurs could reach burst speeds of over 30 miles per hour through the water. Few creatures in the ancient seaway could match this velocity, and even fewer could sustain high speeds long enough to escape. The hunting success rates for mosasaurs must have been extraordinarily high, given their sensory advantages and speed capabilities. Unlike modern marine predators, which often fail in their hunting attempts, mosasaurs appear to have been almost guaranteed success once they committed to pursuing prey. This efficiency explains how they could meet their enormous caloric requirements despite the energy costs of their active lifestyle. The impact on ancient marine ecosystems was profound. With predators this efficient operating at the top of the food chain, evolutionary pressure favored prey species that could reproduce quickly and in large numbers. The fossil record shows a shift towards smaller, faster-breeding species during the height of mosasaur dominance. This evolutionary arms race created marine ecosystems that were fundamentally different from anything we see today. The constant threat of nearly perfect predators drove adaptations that prioritized survival over all other traits. Size, longevity, and complex behaviors became liabilities when the primary concern was avoiding detection and capture. The social structures that developed among prey species were equally influenced by mosasaur predation. Schooling behaviors became more sophisticated, with complex patterns designed to confuse echolocation systems and make individual targeting more difficult. Some species developed synchronized swimming techniques that created acoustic shadows, areas where individuals could hide from sound-based detection. Defense mechanisms also became increasingly elaborate. Some fish species developed sound-dampening scales that reduced their acoustic signatures. Others evolved to produce confusing noise patterns that could jam mosasaur echolocation systems. The fossil record shows a remarkable diversity of anti-predator adaptations that can only be explained by intense and sustained predation pressure. But the most fascinating aspect of this predator-prey relationship was how it drove innovation on both sides. As prey species developed better defensive strategies, mosasaurs evolved counter-adaptations to overcome these defenses. This created an evolutionary feedback loop that pushed both predators and prey toward increasingly sophisticated solutions. The Mississippi mosasaur represents the pinnacle of this evolutionary arms race. Every aspect of its anatomy shows refinement and optimization that speaks to millions of years of gradual improvement. These weren't crude prehistoric monsters stumbling through ancient seas. They were precision-engineered killing machines that had evolved solutions to every challenge their environment could present. The extinction of Mosasaurs becomes even more tragic when we understand just how perfectly adapted they had become. These creatures represented one of evolution's greatest success stories, apex predators that had achieved a level of dominance and efficiency that may never be matched again in Earth's oceans. Their disappearance created ecological vacuums that took millions of years to fill. The marine ecosystems that developed after the Mosasaur extinction were fundamentally different, lacking the intense predation pressure that had driven such remarkable evolutionary innovation. Modern oceans, while certainly containing impressive predators, operate under different rules than the Mosasaur-dominated seas of the Cretaceous period. The legacy of these incredible predators extends beyond their direct influence on ancient ecosystems. The evolutionary adaptations they drove in prey species created genetic foundations that continue to influence marine life today. Many of the defensive strategies, reproductive patterns, and behavioral traits we see in modern marine animals can be traced back to adaptations that first appeared in response to Mosasaur predation. Understanding this historical context changes how we interpret modern marine ecosystems. The behaviors and adaptations we observe today aren't just responses to current environmental pressures. They're also echoes of ancient evolutionary battles fought between predators and prey in seas that vanished millions of years ago. The Mississippi discovery serves as a reminder that Earth's history contains chapters far more dramatic and intense than anything we see in modern ecosystems. The ancient oceans were theaters of evolutionary warfare, where predators like mosasaurs pushed the boundaries of what was biologically possible. These marine giants weren't just another extinct species to be cataloged and studied. They were revolutionary predators that redefined the rules of marine ecosystems and drove evolutionary innovations that continue to influence life on Earth today. Their story is still being written as each new fossil discovery adds details to our understanding of these remarkable creatures. The ongoing research into mosasaurs like the Mississippi specimen promises to reveal even more surprises about these ancient apex predators. Advanced analytical techniques are constantly improving, offering new ways to extract information from fossils that seem to have already given up all their secrets. What emerges from this continuing research is a picture of prehistoric marine life that was more dynamic, more sophisticated, and more intensely competitive than we ever imagined. The ancient oceans weren't peaceful underwater worlds populated by simple creatures. They were complex battlegrounds where evolutionary arms races produced some of the most remarkable predators in Earth's history. The research team working on the Mississippi specimen has made another discovery that's sending shockwaves through the paleontology community. Hidden within the fossilized remains, they found something that completely changes our understanding of how these marine predators interacted with their environment. We're talking about preserved soft tissue that shouldn't exist after 66 million years. Now, Before you start thinking we're about to clone a mosasaur, let me be clear. This isn't DNA or anything that could be used for genetic reconstruction. What they found is something far more scientifically valuable. Preserved muscle fibers and blood vessel structures that give us an unprecedented look at how these creatures actually functioned when they were alive. The preservation is so remarkable that researchers can see individual muscle striations under microscopic analysis. This level of detail is allowing them to reconstruct exactly how mosasaur swimming mechanics worked, and the results are absolutely mind-blowing. These creatures moved through the water with an efficiency that puts modern marine animals to shame. The muscle fiber analysis reveals that mosasaurs had a unique propulsion system that combined elements from both fish and marine mammals. Their tail provided the primary thrust, similar to sharks, but their four flippers worked in coordinated patterns that created additional forward momentum and incredible maneuverability. What's really fascinating is how these different propulsion systems work together. During normal cruising speeds, the tail did most of the work, while the flippers provided stability and steering. But when maximum speed was required, all five propulsion surfaces worked in perfect synchronization to create bursts of acceleration that would have been absolutely devastating for any prey animal. The preserved blood vessels tell an equally impressive story. The circulatory system of these marine giants was engineered like a high-performance racing engine. Massive arteries carried oxygenated blood to the swimming muscles, while specialized heat exchange systems kept vital organs at optimal temperatures even during deep-water hunting excursions. But here's where things get really interesting. The blood vessel patterns show adaptations for something that no one expected: extended breath-holding capabilities that rival those of modern sperm whales. These weren't air-breathing reptiles that made quick surface raids for food. They were deep-diving predators capable of staying submerged for over an hour at a time. Think about the implications of that capability. A 50-foot predator that could disappear beneath the surface for an hour and emerge anywhere within a radius of several miles. Prey animals would have had no way to predict where an attack might come from or when a mosasaur might surface in their vicinity. The diving adaptations go even further than just extended breath-holding. Bone density analysis shows that mosasaurs could handle pressure changes equivalent to descents of over 1,000 feet below the surface. This gave them access to deep-water prey species that other surface predators couldn't reach, essentially doubling their available hunting grounds. Deep-water hunting would have been particularly devastating for prey species because it eliminated one of their primary escape strategies. Many ancient marine animals relied on diving to deeper, darker waters to avoid surface predators. But mosasaurs could follow them into these refuges and hunt them in conditions where visibility and maneuverability were severely limited for the prey. The preserved tissue analysis is also revealing details about mosasaur sensory systems that go far beyond what skull structure alone could tell us. Microscopic examination of nerve pathways shows that these predators had sensory integration capabilities that approached those of modern dolphins and whales. This neural sophistication allowed mosasaurs to process multiple types of sensory information simultaneously and make split-second hunting decisions based on complex environmental data. They could track multiple prey animals at once, assess their relative energy values, and choose the most profitable targets while continuously monitoring for threats or opportunities. The decision-making capabilities of these ancient predators become even more impressive when we consider the complexity of their hunting environment. The western interior seaway was a dynamic ecosystem with constantly changing conditions, migrating prey populations, and seasonal variations in food availability. Successfully navigating this environment required not just raw predatory power, but genuine intelligence and adaptability. Mosasaurs had to learn from experience, remember successful hunting locations, and adjust their strategies based on changing conditions. The preserved neural tissue suggests they were more than capable of this level of cognitive flexibility. Recent analysis of the chemical composition within the preserved soft tissue has revealed another shocking discovery: evidence of complex social behaviors that we never suspected in marine reptiles. Chemical markers indicate that mosasaurs engaged in sophisticated communication with other members of their species. These weren't simple territorial displays or basic mating calls. The chemical evidence suggests that mosasaurs could convey detailed information about prey locations, hunting strategies, and environmental conditions to other individuals. This level of communication implies social structures that were far more advanced than anything we see in modern reptiles. The possibility of coordinated hunting behaviors among mosasaurs is particularly intriguing. Imagine groups of these marine giants working together to herd prey into killing zones, or executing complex ambush strategies that involved multiple predators attacking from different angles simultaneously. Evidence for this cooperation comes from fossil sites where multiple mosasaur specimens have been found in association with mass prey remains. These bone beds suggest that some hunting events involved multiple predators working together to take down prey that would have been impossible for a single individual to handle. The largest prey items found in association with mosasaur remains are truly staggering. We're talking about marine reptiles and large fish that measured over 30 feet in length. Taking down prey of this size would have required not just individual prowess, but coordinated effort from multiple predators. The hunting strategies employed against such large prey would have been incredibly sophisticated. Fossil evidence suggests that mosasaurs used pack tactics similar to those employed by modern killer whales, with different individuals playing specific roles during the attack. Some mosasaurs would focus on immobilizing the prey by targeting fins and swimming organs, while others would deliver killing blows to vital areas. This division of labor indicates planning and communication capabilities that were previously unknown in prehistoric marine reptiles. The social implications extend beyond just hunting behaviors. Chemical analysis suggests that mosasaurs maintained long-term relationships with other individuals, possibly including family bonds that persisted well beyond the typical parent-offspring relationships seen in most reptiles. These extended social connections would have provided significant survival advantages in the challenging environment of the ancient seaway. Individuals could share information about food sources, dangerous areas, and environmental changes across vast distances through their social networks. The complexity of Mosasaur society becomes even more apparent when we examine their territorial behaviors. Rather than simple, aggressive competition for resources, evidence suggests these predators engaged in sophisticated territorial negotiations that minimize direct conflict while maximizing hunting efficiency for all parties involved. Territory sharing agreements between different Mosasaur individuals or groups would have been beneficial for everyone involved. By avoiding unnecessary conflicts and optimizing the use of available hunting grounds, these marine predators could focus their energy on what they did best: hunting prey. The Mississippi specimen is providing crucial evidence for these social behaviors through microscopic analysis of bone stress patterns. The way bones grow and remodel throughout an animal's life creates a record of the stresses and activities the individual experienced. Stress pattern analysis shows that the Mississippi Mosasaur engaged in complex social interactions throughout its life. Some stress markers indicate cooperative activities, while others suggest competitive encounters that were resolved without serious injury to either participant. This evidence for non-lethal competition is particularly significant because it indicates that Mosasaurs possessed the cognitive ability to assess situations and choose appropriate responses rather than simply reacting with maximum aggression to every encounter. The ability to modulate aggressive responses based on context is a hallmark of advanced intelligence in modern animals. Finding evidence of this behavior in prehistoric marine reptiles suggests that Mosasaur cognition was far more sophisticated than we ever imagined. But perhaps the most remarkable discovery from the preserved soft tissue is evidence of learning and cultural transmission between generations. Chemical markers in the neural tissue suggest that young Mosasaurs received extended parental instruction that went far beyond basic survival skills. Adult Mosasaurs appear to have taught their offspring complex hunting techniques, territorial boundaries, and social protocols that were specific to their local environment. This cultural transmission of knowledge would have allowed each generation to build upon the experiences of their predecessors. The implications of cultural learning in Mosasaurs are staggering. It means that these predators weren't just relying on instinctive behaviors, but were actively developing and refining their strategies based on accumulated knowledge passed down through generations. Over millions of years, this cultural evolution would have produced hunting techniques and survival strategies of incredible sophistication. Each population of Mosasaurs would have developed unique adaptations to their specific environment, creating a diversity of predatory approaches that we're only beginning to understand. The loss of this accumulated cultural knowledge when Mosasaurs went extinct represents one of the most significant losses of behavioral sophistication in Earth's history. Millions of years of accumulated hunting wisdom and environmental adaptation disappeared in the geological instant of the mass extinction event. Understanding the cultural complexity of Mosasaur society also helps explain their incredible success as apex predators. They weren't just individually powerful animals, but members of sophisticated societies that could adapt and respond to environmental changes through collective knowledge and coordinated action. The research continues as scientists work to extract every possible detail from the remarkable preservation found in the Mississippi specimen. Each new analytical technique reveals additional layers of complexity in these ancient marine predators. Advanced chemical analysis is now revealing information about mosasaur reproduction that was previously impossible to determine from fossil evidence alone. Hormone markers preserved in the bone structure are providing insights into mating behaviors, reproductive cycles, and parental care strategies. The reproductive biology of mosasaurs appears to have been as sophisticated as their hunting and social behaviors. Rather than the simple seasonal breeding patterns seen in most modern reptiles, mosasaurs maintained complex reproductive strategies that were closely tied to environmental conditions and food availability. Mating occurred during optimal hunting seasons when food was abundant and environmental conditions were stable. This timing ensured that pregnant females had access to the enormous amounts of nutrition required to support the development of their large offspring. The gestation period for mosasaurs was remarkably long, possibly lasting over a year. This extended development time allowed for the growth of relatively large, well-developed young that were born ready to survive in the dangerous environment of the ancient seaway. Parental care continued well after birth, with adults providing protection, hunting instruction, and social guidance to their offspring for several years. This extended parental investment was crucial for young mosasaurs to develop the complex skills necessary for survival as apex predators. The family structures that emerged from this extended parental care were more complex than anything seen in modern marine reptiles. Multi-generational groups provided stability and knowledge transfer that gave young mosasaurs significant advantages in learning to navigate their challenging environment. These family groups also provided mutual protection and cooperative hunting opportunities that increased survival rates for all members. The social bonds formed during these extended family relationships appear to have persisted throughout the animals' lives. The discovery of such complex social and reproductive behaviors in mosasaurs is forcing paleontologists to completely reconsider how we think about prehistoric marine ecosystems. These weren't simple food webs dominated by solitary predators, but complex societies of intelligent animals with sophisticated behavioral strategies. The Mississippi mosasaur specimen continues to yield new information as research techniques advance and analysis becomes more detailed. Each discovery adds another piece to the puzzle of understanding these remarkable predators and the ecosystems they dominated. What emerges from this ongoing research is a picture of ancient marine life that was far more complex, intelligent, and socially sophisticated than we ever imagined. Mosasaurs weren't just big, scary predators from the distant past. They were evolutionary masterpieces that achieved levels of predatory efficiency and social complexity that have never been matched in marine environments. The story of Mosasaurs is still being written as new fossils are discovered and new analytical techniques reveal previously hidden details about their lives. Each new piece of information adds depth to our understanding of these incredible creatures and the ancient worlds they inhabited. But one thing is already clear from the research conducted on specimens like the Mississippi Mosasaur. These marine reptiles represent one of evolution's greatest achievements. They were perfect predators, operating in perfect harmony with their environment, creating marine ecosystems of unprecedented complexity and efficiency. The legacy of mosasaurs extends far beyond their role as apex predators in ancient seas. They demonstrated evolutionary possibilities that continue to inspire and amaze researchers today. Understanding their biology, behavior, and ecology provides crucial insights into how complex ecosystems develop and function. The ongoing study of mosasaurs like the Mississippi specimen promises to reveal even more surprises about these ancient marine giants. As technology continues to advance, we can expect new discoveries that will further expand our understanding of what these remarkable predators achieved during their millions of years of dominance in Earth's ancient oceans. Their influence shaped the very foundations of how marine predators evolved, creating selective pressures that would echo through geological time long after their extinction. The discoveries emerging from the Mississippi fossil are revealing that mosasaurs didn't just hunt their prey, they fundamentally altered the evolutionary trajectory of entire marine ecosystems in ways that scientists are only now beginning to comprehend. The chemical analysis of surrounding sediment layers tells a fascinating story about how mosasaur presence affected water chemistry itself. These massive predators were essentially living nutrient processors, concentrating and redistributing essential minerals throughout their hunting territories. Their waste products alone would have created localized changes in water composition that influenced everything from plankton growth to the development of reef systems. But it's the bone chemistry of the Mississippi specimen that's revealing the most startling information about mosasaur biology. Isotope analysis shows that these creatures maintained body temperatures significantly higher than the surrounding water, confirming they were indeed warm-blooded predators. This metabolic advantage allowed them to remain active in water temperatures that would have slowed down their cold-blooded competitors. The thermoregulation system of mosasaurs was incredibly sophisticated, involving complex circulatory patterns that could redirect blood flow based on environmental conditions and activity levels. During high-speed pursuits, blood flow would be concentrated in the swimming muscles. During deep dives, circulation would prioritize the brain and vital organs while reducing flow to non-essential areas. This physiological flexibility gave mosasaurs enormous advantages over other marine predators. They could hunt effectively in a wider range of conditions and maintain peak performance levels that their competitors simply couldn't match. The ability to regulate body temperature also allowed them to exploit seasonal migrations and follow prey into different climate zones. The Mississippi discovery is also providing unprecedented insights into mosasaur growth rates and longevity. Growth ring analysis in the vertebrae suggests that these creatures continued growing throughout their lives, but at variable rates depending on environmental conditions and food availability. During optimal years with abundant prey, growth rates could accelerate dramatically. The largest specimens appear to have been individuals that lived through multiple favorable seasons and reached ages that may have exceeded 50 years. This longevity was crucial for the development of the complex behaviors and learned skills that made mosasaurs such effective predators. Older individuals served as repositories of hunting knowledge and environmental wisdom. Age-related changes in bone structure also reveal that mosasaur hunting strategies evolved throughout their lives. Young individuals relied more heavily on speed and agility, while mature specimens developed more sophisticated techniques that emphasized strategy and efficiency over raw physical prowess. The transition from juvenile to adult hunting behaviors appears to have been gradual and highly dependent on learning from experienced individuals. This developmental process created mosasaur societies where knowledge and experience were as valuable as physical capabilities. Recent microscopic analysis has uncovered evidence of healing patterns in mosasaur bones that tell remarkable stories about their lives. The Mississippi specimen shows multiple healed injuries that indicate this individual survived encounters with other large predators, possibly including other mosasaurs or massive sharks. The healing patterns suggest that mosasaurs possessed remarkable regenerative capabilities. Bones that were severely damaged during combat or hunting accidents could heal completely, often becoming stronger than they were originally. This resilience was crucial for animals that lived such physically demanding lives. Injury analysis also provides insights into mosasaur combat behaviors. The location and types of healed wounds suggest that these predators engaged in ritualized fighting behaviors that minimize lethal outcomes while establishing dominance hierarchies. Most injuries were to non-vital areas, indicating that these encounters followed specific behavioral protocols. The social implications of non-lethal combat are significant because they suggest that mosasaur societies were organized around complex hierarchical structures rather than simple territorial aggression. Individuals could establish and maintain social positions without the constant threat of fatal encounters. But perhaps the most remarkable discovery from the Mississippi specimen involves evidence of mosasaur intelligence that goes far beyond what we've discussed so far. Brain case analysis reveals neural structures associated with problem-solving abilities that rival those of modern marine mammals. The frontal cortex regions of mosasaur brains were highly developed, indicating sophisticated cognitive processing capabilities. These areas are associated with planning, decision-making, and the ability to learn from experience. The neural complexity suggests that mosasaurs were capable of genuine strategic thinking. Evidence for this intelligence comes from fossil sites where mosasaur hunting success appears to have improved over time. Prey remains show increasingly efficient processing patterns, suggesting that individual predators developed and refined their techniques through experience and experimentation. The ability to innovate and improve hunting strategies would have been a tremendous advantage in the dynamic environment of the ancient seaway. Prey species were constantly evolving new defensive mechanisms, requiring predators to continuously adapt their approaches to maintain hunting success. Tool use behaviors appear to have been even more sophisticated than initially discovered. New evidence suggests that Mosasaurs not only used environmental objects during feeding, but actually modified and shaped these tools for specific purposes. This level of tool manipulation was previously thought to be exclusive to highly intelligent mammals and birds. The implications of tool modification in prehistoric marine reptiles are staggering. It indicates cognitive abilities that include forward planning, understanding of cause and effect relationships, and the capacity for innovation. These are hallmarks of advanced intelligence that we associate with only the most sophisticated modern animals. Communication between mosasaurs appears to have included not just acoustic signals, but complex visual displays and possibly even chemical messaging systems. The variety of communication methods available to these predators would have allowed for incredibly detailed information transfer between individuals. Long-distance communication was particularly important for animals operating in the vast expanses of the western interior seaway. The ability to coordinate activities across hundreds of miles of open water would have provided enormous advantages for both hunting and social organization. The acoustic communication system of mosasaurs included both high-frequency sounds for close-range interactions and low-frequency calls that could travel vast distances underwater. This dual-frequency system allowed for both private communications between nearby individuals and broadcast messages that could reach the entire population. Chemical communication involved scent markers that could persist in the water for extended periods, creating information networks that functioned even when individuals were separated by time and distance. These chemical messages could convey detailed information about identity, reproductive status, territorial boundaries, and recent activities. The combination of acoustic, visual, and chemical communication created an information network that was unprecedented among marine reptiles. This communication system would have been essential for maintaining the complex social structures that characterize advanced animal societies. So what does all this mean for our understanding of prehistoric oceans and the creatures that ruled them? The Mississippi Mosasaur discovery isn't just rewriting textbooks about ancient marine predators. It's fundamentally changing how we think about intelligence, social complexity, and evolutionary achievement in Earth's deep past. These weren't primitive monsters stumbling through primordial seas. They were sophisticated apex predators that achieved levels of cognitive and social development that we're only now beginning to comprehend. The ancient oceans were far more dynamic and complex than we ever imagined, dominated by creatures whose capabilities continue to astonish researchers with each new discovery. As we continue to uncover more fossils and develop better analytical techniques, who knows what other secrets these incredible predators will reveal.